good presentations. Will be paper presentations. Each of them will be 20 minutes, but I assume there will be like 50 minutes presentation, a couple of minutes for questions. So please stay awake, stay active. And while Leonard, I guess, yes, and I guess you're from Stuttgart University. I had to look it up from the agenda. It was not obvious to me, but he's playing a home match. I guess, I hope a winning one. I think both the German and Dutch team lost. Yes, that was terrible. Fine. So let's not bring it up. Let's not spoil our good moods and listen to the talk, which is about unsupervised automated pre-processing. And I'm very curious what you guys came up with. So please get started.
So, now it's on? Yes. All right, thanks for the nice introduction. Yeah, I'm Leonard and I'm going to talk about unsupervised automated preprocessing and especially the role of meta features and data characteristics. But let's first start with a general setting. So usually everybody who has a data set wants to gain some insights and knowledge. And of course there are many different ways to obtain these insights and knowledges. For example, you could use supervised machine learning. Today you would use a lot of agents and LLMs. You may use unsupervised machine learning or even some data products. But the main thing is there's always an analytical process in between. So you always need to do something to obtain your insights and your knowledge. And in the real world, there might be some problems you discover because the real world data is often in a bad shape. And if you give the analytical process garbage in, then you will get garbage out and no insights and knowledge. But yes, let's look at a few examples. What can go wrong or what usually go wrong if you're dealing with such data. Consider this first example where we just take our data set very naively as a new data scientist. We put it into the algorithm and then the algorithm crashes. Why? Because we have missing values in the data set. And many algorithms cannot deal with missing values. We remember that, apply our algorithm, it runs again, but now there's no meaningful structure to cover because we forgot about scaling. We remember scaling, apply scaling, and now some outliers become visible, and still we don't have a good result. Finally, after these many steps, we are, for this small example, done and have a good result. So there are a lot of things to consider during such analytical processes regarding the data quality. And if you do not care about data quality, you probably won't get any meaningful insights and knowledge. So let's make this process a bit more concrete, and I also want to introduce the focus of our work. We now have learned a bit more, and instead of naively trying things out, we have exploration and a pre-processing phase. But let's start with the data set. In this work, we are only considering tabular data sets, and more precise, only numerical tabular data sets. So just consider a big Excel sheet with only numbers in it. During the exploration, we want to find all these data problems. And from now on, maybe a bit in the direction from the talk in the morning from Simon, I will call them data characteristics. So something in the data like missing values or outliers are data characteristics. If we have now found them, we of course want to remove them or want to pre-process our data, because then we can do our analytical machine learning task, and as our title maybe suggests, we are in the unsupervised domain, so we are doing clustering here as an example. And then finally we can get our answers. Well, even having this process, in the real world it's not that easy, and you need to answer a lot of questions during that process. And if you do it on your own, you need to answer them by hand. So for example, during the exploration phase, you should know what you're actually looking for. So what data characteristics do I have? If I know that, I then need to pre-process my data, and it's often completely unclear which method should I use, which parameters have these methods, and if I have multiple data problems or data characteristics, it's also unclear in which order should I execute my pre-processing pipeline. After the cleaning, then I need to do the actual clustering, and again, there are many different algorithms, the parameters, and in the unsupervised domain, there's also not even clear which evaluation score you should use. And of course, if you have done this many times, you have gained some experiences and become quicker and see a lot of things faster, but maybe you also forget about things and remember it only while doing it again. And what we usually want to do when in such cases is we want to automate it. We want to create a system that does all this thinking and all this decision making for us. Or maybe we ask ourselves, is there a system that does this for us? And in the clustering domain, there are some very interesting work that automatically suggests you a clustering algorithm, the parameter and the evaluation score for a given new data sets. And that's then called automated machine learning for clustering. The problem is with these other parts, it is not so clear. And in the unsupervised domain, there is no approach that can fulfill this. So for example, an automated approach would need to identify the data characteristics, similar to a human. Then of course it needs to automatically pre-process the data. And it would be really nice if we could store the data in some way and learn from our made experiences. And there's one approach or one general concept that has worked very well or is working very well in the domain of automated machine learning, which is called meta-learning. And we don't want to, in a bigger picture, apply this or think about applying this to all the other problems we have here. But what is meta-learning? This is a bit of a simplified example mapped to our current problem. So consider we have known data sets, and we've gained them from experiences. We know these data sets, and we know what has worked for these data sets. We then can take this knowledge and these experiences and create a knowledge base. As a simplified example, with the pre-processing pipelines that have been applied to these data sets, and the quality score, how well these pre-processing pipelines have worked out. And then for a new data set, we can provide them to something like a meta-learning system. And this meta-learning system then looks into the knowledge base and tries to find similar data sets. Because the assumption is, if we have a similar data set in our knowledge base, and we have a pre-processing pipeline that works well within for this data set, it may work well for the new unseen data set because they're similar. And this is also the output, or possible output of such a meta-learning system that then can provide the user or the data analyst with a selection of presumably well-working pre-processing pipelines. The problem is the finding and the similarity. So we need a way to somehow compare these unseen data sets to the data sets encoded in our knowledge base. And one option to do this are meta features. And a meta feature can be basically everything. We define it as something that results in a number. So remember the data set from earlier? And our data set has data characteristics. Those are contained within the data set. So they are part of the data set. And a meta feature is now a calculation on top that describes or measures the data characteristics. And as I said, that could be almost everything as long as we can somehow use it for comparison. So a very basic one is the number of rows or the number of columns of this data set. But there are also some statistical ones like the skewness of a certain feature and so on. So now with all this information gained, I come to our contribution. But one thing first, of course, these whole concepts of data characteristics, pre-processing, meta features, meta-learning are not new and that are not concepts we came up with. They exist for decades, some for decades, but no one has yet looked into how we actually could connect all these. So we want, and that's why we are focusing on this first exploration phase, where we ask ourselves how can we identify data characteristics with meta features. And this connection hasn't yet been done. Usually they're using just a lot of meta features as a whole set and hope the relevant ones will be there and I will find all my characteristics. In order to be able to find these connections and sorting out, we went to the literature in the first step and asked ourselves what are the pre-processing relevant data characteristics for clustering. Because first we need to know what we are looking for. After that, we mapped them to existing meta features based on the literature and based on their mathematical foundations of the calculation of these meta features. And in the third step, then we assessed how useful these meta features are, where are the downsides, where are the advantages, where still work to do. But let's start with the first contribution. So we identified 15 data characteristics, and for better understanding and just in general, they can be grouped in 3 different levels. And I won't discuss every data characteristic in detail, but I will briefly talk about the levels. So the first level is the dataset level, we have data characteristics that affect the whole data set. The second level is the feature level. Those are data characteristics like missing values that only affect one or multiple features, but not the whole data set. And lastly, a bit more specific one, a bit more one that is more focused on our general problem in machine learning is the clustering level. So for example, there are data characteristics like clustering overlap. We want in clustering to discover meaningful structure in the data and want a good separation of the data. And we have a lot of overlap. This is usually very hard for clustering algorithms. So it would be nice to have such things not in our data when applying it to the clustering algorithm. And of course, these data characteristics are defined and motivated in much more detail within the paper. But for now, we have these data characteristics, and the next question is, well, what meta features are out there? How can we measure these data characteristics? And I will provide you with this brief overview graphic, where we have in the middle the levels from earlier, from right now, the feature level, cluster level, and dataset level. And on the gray circle here, the already mentioned data characteristics like outlier or like missing values. What is now new is the meta features outside that we have identified as somehow maybe or maybe not belong to the certain data characteristic. And of course, there's no time to explain everyone in detail, but I will provide one example of a meta feature that might be a bit counterintuitive and is an example why it's not always that clear, or why the choice is not always that clear. For that, again, consider cluster overlap, as shown earlier. And within the cluster overlap, the meta feature silhouette score. So those of you who have done a lot of clustering should be familiar with it. It just tells us how good is our cluster separation. And for that, we need a provisional clustering. In more detail, it compares the distance of the points within a cluster to those outside of the cluster. And just as a result, how do we interpret the result? If we get a very low value of this silhouette score, we have usually in clustering overlap. But this is more or less a hint towards this overlap. It does not tell us by how much it overlaps or which clusters are overlapping. So we have this mapping, but at the same time with the example we notice, okay, even if we have meta features that may help us with this data characteristic, it's not always that clear by how much or where the problems are. So in the third step, we assess the usefulness of these meta features. And in order to be able to, we define 4 dimensions to assess how useful the meta features are. The first one is to what extent does the meta feature measure the actual characteristic? Is it a direct measure from the data, or is it more like a hint like the silhouette score? The second one is the grounding, so how can I compute the meta feature? Can I again look directly in the data and easily compute it, or do I need to make more assumptions or even provide a provisional clustering or something like that? The third one is how actionable is the meta feature. After calculating it, after knowing the characteristic is there, do I know how to preprocess it? Does the meta feature tell me what to do next after noticing that I have a problem? And the last one is the context robustness, which tells us by how much does the value depend on some thresholds or choices. So you as a user calculate the meta feature, and therefore if you need to define several thresholds, it's a problem. Because you need to make choices, and that may influence the data. And in order to be able to define this, we have 3 levels of fulfillment, from 1 bar, which is not so good, to 3 bars, which is quite good. So, and here's a big table with a lot of data characteristics, and the meta features are not even on there. They are just the data characteristics leveled, and the evaluation of the meta features grouped by these dimensions I just showed earlier. And again, there won't be a detailed discussion about it, but we have identified 3 classes, so class A, B, and C. And those classes in general tell you how good are you, or how difficult is it to build a meta-learning system with these meta features. And as you see, class I, if you're usually dealing with such data characteristics, you should be good to go. They're easily calculatable, they're easily understandable, and you should be easy to detect these data characteristics. Class B, it becomes a bit more vague. So we have these things like outlier or sparsity, where you need to make statistical assumptions. So it becomes not so clear, but with a bit of a knowledge how to calculate it, you should still be able to detect it. The real problem lies in class C, where we have a lot of assumptions, where we need to think a lot about how to calculate and really need to know what we are doing, because we need clustering algorithms or anything to actually calculate it, and it really depends on certain values or algorithm choices. So class C is the area where you need to be very careful if you do meta learning, or where there's even maybe a need to create new meta features to better capture these data characteristics. And with that, I will come to the end. Again, here are the contributions. And of course, this is a first literature-based and mathematical-based assessment, but the intuitive next step is an empirical evaluation. So we are planning, or we are currently doing, taking real-world data and assess how useful these mappings are and where the actual problems are, if they are as we expect, or are they new or other problems. And the overall goal is, of course, to map this or to embed this in a preprocessing or meta-learning system that automatically recommends preprocessing pipelines. And yeah, for more details about this work, or if you want to discuss the overall topic of automated preprocessing, it will be at the poster session, so I'm happy to discuss any details there. Thank you.
Thanks for the very nice presentation, and perfectly well on time even. So is there any questions from the audience?
Great presentation. Quick question if your data is structured and you have missing data, right? How do you know the outliers are reliable? I mean, for example, let's say there's a lot of data on potassium values for a certain patient population. Everybody knows that potassium values lie between 3 and 6, right? If your outlier model or your missing data solution tries to put the value above 6, right? That means the patient is going to be dead, right? That's typically how the potassium values have to be between 3 and 6, but even the best random forest or whatever missing data algorithms out there will put them values way outside the range. So there's always issues there where the domain knowledge has to be included, which means that you have to ingest the clinical guidelines, for example, or any guideline for the matter, right? Likewise, if you have a machine, the machine has specifications. Those specifications defined in some sort of a governance document or a compliance document. If the values are away from that, then it doesn't make any sense for the data processing to be done. So I don't know how we're going to address that.
Okay, yeah, two parts. So this is then more on the preprocessing side, like imputing missing values, not on detecting them. And yeah, of course, this is a problem, and domain knowledge is extremely important. In these automated approaches, usually there is not that much research in the unsupervised domain, and we are starting without considering domain knowledge, but definitely planning in the future to include it. But I don't know if for this, I think, rather simple example, a missing value can be computed by taking the mean or the average of the values of the same feature where of those who are not missing. Usually if your data has no errors, but you mean the relationship between missing values and outliers. Yeah, that's a real problem in this case. And I would say without domain knowledge, it's make it really hard to, But I think you still will be able to separate your clients into groups. What you should not do with such a system is maybe generating a medication plan, so that would be really dangerous.
Okay, I guess there's time for one more short question, I hope, and a short answer.
Thank you a lot for the really nicely illustrated presentation. A little bit connecting to this question, because I followed really nice, but slightly mocking, because in your case, the meta features, you also define them through expert knowledge, through your knowledge basically on what does it not slightly only move the problem basically of, let's say, knowing which worked well for which pipelines, that more knowing which meta learning parameters could work well in this case?
I'm not 100% sure if I understand the question correctly, but yeah, so of course there's some expert knowledge involved, but we really went into the literature, and it was a lot of effort because people writing about stuff, which meta features worked well in certain scenarios. The problem is usually they focus on a very small use case. Like we have built a very complex system just to detect outliers. And then, okay, how does it generalize and such stuff? If you mean by that how do I say it? That the meta feature selection might be biased towards my knowledge, yes, possibly. That's why we are planning this empirical evaluation.
Okay. No, I get it. I mean, it's difficult to. How do you find meta features? Like, if it does not come from some research, for example.
Well, thank you very much, and you can follow up the discussion, obviously offline later on. So thanks again for the presentation. The next presentation